Hello, welcome to the second video on understanding this amplifier for this old Rock-Ola jukebox. And if we remember where we were when we left before, we had the rectifier tube, and the rectifier tube had an input from the transformer, came out to a filament. It actually had two filaments, but it doesn't really matter. And there was a plate, a pair of plates. Actually, one would take current during the positive portion of the waveform, and one would take current during the negative portion of the waveform. So if we look at just, your typical sine wave coming in, what was happening was that during this positive portion, this plate would be positive. It would get a certain amount of charge, and that voltage would be enough to attract electrons off of the filament and onto that plate. So as a result, the output of this is during the positive cycle, it would let the current come out. That's obvious enough. During the negative portion of the waveform, let's say this part down here, then this plate would wind up being negative, but this plate over here would be positive, and so electrons would leave that filament and come over on to that plate. And so as a result, this portion of the waveform would also go through this rectifier. And so this is rectification. We've changed this AC waveform where the current is alternating. At 60 hertz, it's switching from going in that direction to that direction at 60 hertz. We've changed that from alternating current to direct current. Now it's certainly a pulsed waveform, but it is direct current. The current is always going in the same direction. Okay, so when we first flip on this particular circuit, what will happen, based on what we just talked about, is if we look at the voltage as a function of time here, during the first waveform, the voltage will come up, and it will eventually reach a maximum. Okay? And the question is, why does it reach that maximum? Why doesn't it just keep going up? Well, if you remember, what we're doing is, with every electron that leaves, whether it leaves in the positive cycle or the negative cycle, or for whatever reason that leaves, for every electron that leaves this little loop of the circuit, the voltage of this little loop of the circuit goes up by 1 electron. And so you move enough electrons and you get this voltage to go up as high as you want. But at some point, the voltage of this circuit with the filament begins to approach the voltage of this plate during the maximum. And so as more and more charge leaves, this voltage goes, the voltage of this portion of the circuit goes higher and higher. And when that voltage of this filament approaches the voltage of the plate, either plate, during the positive cycle, the electric field here is going towards zero. And at some point, there's not enough electric field to strip electrons or to get electrons to migrate from this filament area over to the plate. And so that's why we reach this voltage. And this voltage is going to be, nominally, whatever voltage is being applied to either of those plates. So in this case, this is the order of 350 volts or so. Okay, so that's why this eventually, just without drawing current from this will eventually just come up and reach a steady state. Okay, I mentioned in the last video that I generally like to think of current as being positive, the flow of positive charge, but when I'm working with vacuum tubes, it makes more sense to think of the flow as being the flow of negative charge, simply because the electrons are doing the work in this. And of course, whether we think of current as being the flow of positive charge or negative charge is completely arbitrary. And what we mean is, let's now say that we are tapping onto this circuit. So instead of just charging this circuit up, we're actually going to be taking current off of this. And so normally we would say, okay, we've got some amount of current, I, leaving this circuit. And when we say that we have a current I leaving this circuit, what we mean is that we have positive charges that are going in that direction. But of course we can just as easily think of, well, instead of positive going in that direction, we have negative charge going in that direction. And of course it's these electrons, this negative charge going in that direction, that eventually find their way down to this filament and then get stripped back off again. So in all the rest of the circuit, wherever we're connected to earth or to ground, because you remember this transformer, when it stripped these off, it was eventually putting those onto earth. And they go through the rest of the circuit and come back, or in this case, actually to the chassis. So it was taking off, because both of these were then connected to the chassis like this on this side of the transformer. Here's our core of our transformer out here. So when they were going into this plate, they were coming down here and going into the chassis. When they were going to that plate, they were coming down here and going to that chassis. Somewhere else in the circuit, we're connected to the chassis, and the electrons are coming off of that, going through the circuit, doing whatever business they're doing. They wind up back over here and getting pumped back out of the filament again. So that's our circuit. We're going into the chassis over here, and the electrons are coming out of the chassis here. But I'm going to flip back over to talk about, since I'm done talking about this electron tube or this vacuum tube for the moment, I'm going to talk about charge as being the flow of positive, or current being the flow of positive charge. Okay, so back to our little basic circuit here where we have our rectifier. On that rectifier we have charge coming off. Our rectifier is giving us a nice charging waveform, and then once we get up to that final part, it would level off. Okay, now we start drawing current off of this. And so if you remember our original waveform, our original AC, we had full wave rectification, and so our pulses look like this. And as we draw current off of this, what we would see is that instead of completely charging up, depending on how much current this portion of the circuit can produce at any one time, we would see that as we are following this first portion of the waveform, and we can produce current faster than we're drawing it, our voltage would look pretty much the same. But if we got to the top of the first waveform, let's say that occurred right here, the top of the first waveform, what we would see, if we're drawing current, and we would essentially follow this back down again, because there's no ability for this circuit to store anything. And so our output voltage would just start to drop as we pulled current off of this. And as we went back down to zero on the waveform, we would go back down to zero on our output circuit. And so we would wind up getting a voltage output that essentially follows our input. Because other than the electrons in the free space here, there's no ability for this circuit to store any charge. So what we would wind up getting is we would see our first positive waveform, and then we would see our second waveform, the second half. And if this has no ability to store charge, this is what our output's going to wind up looking like. It's going to go up to the peak voltage, come back down, go up to the peak voltage, come back down, and so forth. So we have to apply filtering to this. And well, the first element of our filtering that we want to apply is a storage capacitor. So on this output, we put a very nice large capacitor here that allows this circuit to store some amount of charge between these waveforms. And so this is called a capacitor input filter, because the first element that the rectifier sees when it comes in is a capacitor. And that would be in contrast to an inductor input filter. So this is a capacitor input filter. And in our case, this capacitor is about, I think, 14 microfarads. Okay, what that capacitor does for us, if we look at the same waveform with the capacitor, it charges up pretty much like before, but now instead of following this waveform as we take current off during the discharge, This follows more of a gradual waveform until the point that we get back up to whatever our voltage is. So if it follows this waveform until it gets to about right here, at which point we stop charging because our voltage being applied in our circuit is less than the voltage out here, so we stop charging. Then we come over here, we're not charging until we get back up to this voltage, at which point we start charging again. We follow that up, and then we would start discharging. And then we follow the next one up, and then we would start discharging. So with this storage capacitor, it allows us to have a voltage that is up here nicely where we want to be operating. You know, somewhere in this case it's 320 volts is what this circuit operates at. So at 320 volts, so we now have this waveform that's bouncing around somewhere up here around this 320 volts. And this storage capacitor is what gave that to us, so that during the periods of charge, we charge up this capacitor. During the periods that this rectifier isn't able to give us any current, we draw current out of that capacitor, and it helps carry us through to the next one. Okay, well, we can't make this capacitor as big as we want. You know, the bigger we made this capacitor, the more storage that we would have here. But there's a couple of things. The bigger we make this capacitor and we move this line up, the bigger the capacitor, the smaller the area here that we're taking current from our peak. So if our capacitor is very large, it means our rectifier has to do all of its business, all of its work in very narrow range of this peak. And so we want to have some amount of difference between the voltage of this circuit and the voltage that we're operating, so that we widen how, during what fraction of the peak we're actually taking current out of this. And so the rectifier doesn't have to work quite as hard the wider we make that. Okay, so let's say that this is where we want to have our, during the period of time we want our rectifier to be taking current. The second reason we can't just make this capacitor as large as we want is that when we first flip this circuit on and we're at zero voltage everywhere, this capacitor, if it's too large, it'll take too much current out of this rectifier, and we could damage this vacuum tube by pulling too much current, because essentially when we first turn this on, this looks like a short circuit to this rectifier, and so large amounts of current will be coming out of that rectifier and trying to charge up the capacitor very quickly. And so if you go back and you look at the graphs for this tube, and this is a 3U, no it wasn't, it was a 5 volt, 5U 4 glass. If we look at the curves for a 5U 4G running into 320 volts or 350 volts or so, it'll think, I'm pretty sure it told us that the biggest that should be is 40 microfarad for this output capacitor. We start to get bigger than that and we can draw too much current. And so they're fairly conservative here with the 14 microfarad. Now, of course, this tells us why we have to take care of these electrolytic capacitors. Over time, we lose our electrolyte in this capacitor. It stops functioning. And so then, instead of the amplifier getting at least a constant voltage that has a lot of ripple on it, it starts following this type of a waveform, and this is essentially what we start feeding our amplifier with. And as we feed our amplifier with this is where we get our 60 or 120 volt or 120 hertz hum, because every time essentially the amplifier is shutting off during these periods of time where there's not enough voltage to run it. So it's running during this period of time and then it shuts off, and it runs during that period of time and it shuts off, and it runs during this period of time and it shuts off. And so in the worst case, the amplifier actually completely has it does not have enough power to run during these little valleys. In a better case, it continues to get voltage, but somewhere in this filter, this noise or this ripple makes it through all the way into the amplifier, and so we're actually then hearing that ripple in the amplifier. So that's why when we recap these amplifiers, we're replacing these electrolytic capacitors, because over time they dry out, they lose their ability to store this charge, and then we get this hum in our amplifier, and that's what we're trying to do. That hum is very bad. You can see that it stresses everything. And not only is a hum, but it also stresses this rectifier, and it's stressing all of our tubes downstream and all of our magnetics also, because we're jerking this thing off and on at the 60 hertz. Okay, so back to our basic circuit here. We've got a rectifier, we've got current coming off of this. We put in a storage capacitor here. This is going down to the chassis or to earth. This provides our storage of power of electrons. Then in the next step in the filter, we come out and we have an inductor. What this inductor does, this inductor has a magnetic core, just like any transformer. This current passing through this creates a magnetic field, and the inductor does not like any current to change. Once it creates this magnetic field, it prefers to keep that magnetic field, or if it doesn't have a magnetic field, it prefers not to create a magnetic field. So basically, the inductor likes to stay in steady state in current. Where if you want, you can think of the capacitor as liking to stay in steady state in terms of voltage. So it likes a fixed voltage. If the voltage is 0, it likes to keep it 0, and it'll suck in charge as fast as it can to keep it 0. And if it's any other voltage, it'll accept or reject charge as quickly as it can to try to keep that voltage at 0. The inductor does not like a change in current. So if we look at our waveform as it comes out of the capacitor, remember we have this ripple up here. Well, this ripple in voltage would lead to a ripple in current. So as we get higher voltage, the circuit down here, if it has a constant resistance, would take more current, and then here it would take less current, more current, less current. But this inductor fights that the whole way. So as this circuit would naturally like to ripple up and down in terms of voltage or current, the inductor fights any change in the current, and that it effectively filters down this ripple, so it gets rid of some of that ripple. And the way it gets rid of some of that ripple is we add another capacitor downstream, and so during periods when this voltage would be going up, and so the current would be going up, this inductor fights that, and it tries to maintain that current at a constant value. And so the effect is that if with this LC, so this is an inductor L and this is another capacitor, so we basically have followed our storage capacitor with an LC filter, and so that LC filter has the effect of reducing that ripple. So this is actually a storage capacitor followed by an LC filter, and people generally, they just love naming things after pi, so they'll call this a pi filter, because in some you can think of this as, it kind of looks like a pi. If this is where our inductor is, and these are our two capacitors, so it kind of looks like pi, and so people will call this a pi filter. Okay, so we have our storage capacitor followed by an LC filter, gets rid of our ripple. Now, the LC filter has some advantages over just an RC, which we'll see comes next. The inductors are theoretically lossless because, except for the resistance they have. The inductor, once it starts passing current, it does that very efficiently, so it's not dissipating a large amount of power. This pi filter, this capacitor input filter, gives us a higher voltage on the output than if we didn't have this capacitor. If we came in and had our inductor first and then a capacitor, so we get a little bit higher voltage out of this circuit. But the inductors are bigger. That's one of the big magnetics you see on the top of the amplifier, and so as you can imagine, this inductor costs more than equivalent resistor. Okay, so during periods of time that we're charging this up and the inductor wants to keep its current flat, it draws what it can from the rectifier, and then when the rectifier isn't contributing anything, this inductor will then continue to suck current out of this capacitor in an effort to keep its current as a constant. But then, of course, as it sucks charge out of that capacitor, the voltage here goes down, and eventually that current then would fall down. So it's not perfect, but of course the storage capacitor, the inductor, and the second capacitor do a tremendous amount of reduction in that ripple. After this LC filter, if we look at the actual circuit, this is their B plus right here. So Rockola chose to feed the speaker transformer, the output transformer, directly from this capacitor. And so this is very unfiltered. This is just some voltage with a tremendous amount of ripple on it. They then go through an LC, and after that LC, they then have an RC filter. So they have a resistor out here, followed by another capacitor. So this is their RC filter. And at this point is where they take off for the screen on the push-pull amplifier. They then go through another RC, and at this point they then go into the let's see, this is the B plus for the initial amplifier and also the bias for the push-pull. So this is the most filtered. Of course, here they've gotten rid of almost all of the ripple. This has a little bit of ripple, and this has a lot of ripple. Okay, so the last thing we want to talk about is this RC. How does the RC, the LC is very intuitive because the inductor does not like a change in current, and so you can see how not liking a change in the current would allow this capacitor to provide any makeup current, as well as shunt any AC to ground, because remember the AC will essentially go through this capacitor, but any ripple will go through this capacitor and be shunted to ground. Okay, so we're almost done with this circuit. Let's look at this RC, the last two stages of this filter. So an RC filter, what the resistor does is it preferentially burns off the peaks of the ripple. And I know that sounds odd, but we know that the power dissipated through a resistor is equal to V squared over R. So if we look at that current or the voltage, let's say we've got some amount of ripple on it. Let's say this is our average right here. And so the current going through this resistor, the DC component, or the average steady state component, is going to burn off some amount of power. And that's going to be given, this voltage, we square that, we divide by that resistance, and that's how much power that all of this is going to burn off. But this area up here, see, this goes with the square of the voltage. So any extra voltage that we apply to that, the power is dissipated with the square of that. So my argument is that these regions of higher voltage or higher current are being burned off at a higher rate than the average. And so essentially what's happening is these peaks of whatever noise is on this gets dissipated stronger than the rest of the bulk of the current. And then these capacitors, this one and this one, they serve two purposes still. One is to act as a reservoir for the current, and the other is to shunt AC through to ground. So AC goes right through those, gets shunted to ground, and they also are able to act as a reservoir for the circuit. So between those two, between burning off preferentially the higher voltage spikes or peaks on that circuit, on the current that's going through that circuit, and the storage capacitor, these RCs further attenuate any ripple that's in that. And then this is the B plus for the 76. This point comes off is the screen on the push-pull, and it's the field on the speaker. And then let's see, this is the B plus for the push-pull. Okay, in terms of voltages, right here we have 320 volts. Down here at the end, we've got 245 volts. And right here we have 260 volts. Okay, so we've got a 15 volt drop across this. And we've got a 60 volt drop across this. Okay, so we know that from Ohm's law, V equals IR. So I want to figure out how much current, how much power we've got going through this resistor. This is a 1K and this is a 5K resistor. Okay, so we've got a 60 volt drop, and we've got 1 K resistor. So we've got 60 milliamps going through that one. Here we've got a 15 volt drop and a 5K resistor. So here we've got 3 milliamps going through that. So the amount of power that we're dissipating in that is equal to 60 milliamps, and our 1K again is, I'm sorry, not one, IV. So 60 milliamps times 60 volts. And that's 3,600 milliwatts, or 3.6 watts. So that's a decent resistor. That's 3.6 watts. And then this one over here is 3 milliamps times 15 volts. So 45 milliwatts. So that one's just a little, probably a little quarter watt resistor. Okay, well that's all I wanted to say about this circuit. We have we know now how the filter works, why we're doing all this filtering. We have the voltages. If we decide to replace those resistors, we know what wattage we need, and we know what voltage of capacitors we need. These all need to be 600 volt capacitors. And then we know the capacity on these capacitors. They're given. This is a 14 microfarad, and this is an 8 and an 8 and an 8. Okay, so that's it for this circuit, and next time we will look at the input from the pickup, and I hope that you learned something from this, or at least I hope it was useful. Okay, thanks for watching. Bye.